Hey Shaler area, welcome back. This is note video number 5, and today we're going to be talking about gases and how they behave. We're also going to mention 4 new scientists that you're going to have to know their names and what they did. So we've already discussed that gases lack definite volume and they lack a definite shape, but those properties can change. They're very flexible because they aren't static. They're not stuck in those things. So the volume of a gas can change, and its temperature can change, and its pressure can change. So we're going to talk about these 3 variables and how they impact one another with a gas. So remember that all things are made of matter. So the particles that are in gas, we'll just say the air around you right now, assuming you're in a room that's, room temperature, 20 degrees Celsius is 70 degrees Fahrenheit. One of those temperatures you're supposed to remember. The average speed of the gas molecules is 500 meters per second. That's really fast. That's twice as fast as an airplane. That's really, really fast. And when we talk about air pressure, now it's really, really fast, but remember, they're not going really far. It's not like they're actually moving 500 meters away from where they're starting in 1 second, because they can't, because there's other molecules around them that they would run into on the way in any given direction, and they bounce off and careen. So they're moving really fast, but they don't actually move really far in any one direction before they run into something. Air pressure, when we talk about pressure, since students sometimes have a difficult time envisioning the gas around us as being completely filled with particles, sometimes they don't quite understand how the pressure works either. So air pressure is what you feel when all of those particles in the air around you are running into you all the time on the outside of your skin. So you're getting slammed into by carbon dioxide molecules, we'll say at 500 meters per second, and oxygen gas molecules, and hydrogen gas molecules, and water molecules, and methane, and all kinds of other particles are just running into your skin really fast. They do have different speeds depending on their sizes, but still, all really fast. The reason you don't feel them and don't get smacked around by them is because 1, they're really small. 2, you're getting hit from all sides equally, so they balance. And 3, your body just gets used to them. So the way our nervous system works when we are bringing in information from the outside, and our brain like decodes it to figure out what our reality is. If there is a information stream coming in that's constant, your brain filters it out, because if it's constant, then it's not dangerous, or at least, that's the way your brain interprets it. So it doesn't have to worry about it, so it just kind of ignores it. They have really interesting research projects where they'll put a pattern on contacts and have people wear them, and then they can see this pattern in front of their eyes, but after a couple minutes, it just goes away. The brain just literally stops seeing it. And the same thing goes with like your pressure. So also, you have gas inside of you pushing out as well. Gases in your blood and gases, in your belly and your lungs and that kind of stuff. So you have pressure on the outside pushing on you, and you have pressure from the inside pushing out. And that's what happens when you end up going into outer space. If someone were to leave a spaceship without a spacesuit, the pressure on the inside of their body is now what it would normally be, but it's no longer being balanced out by the air molecules running into the outside of the body. So the inside of the body, greater pressure, that's what makes you kind of balloon up in that kind of a situation. Here's our first scientist to discuss. This is Blaise Pascal. And he is the person that gets the honor of having a unit named after him. And the formula that you need to remember is P is F divided by A. The P is pressure. And pressure is equal to the force divided by the area. So pressure is a force, it's a push, so you're always pushing on pressure. There can be negative pressure as well, but it's be more of a pull. And divided by the surface area that the substance is on. So if you're standing on the point of a pin versus standing on a sheet of 8x10 plywood, which one would have the greatest amount of pressure? On the pin, because you're dividing it by a much smaller surface area. Now, Pascal did a lot of really interesting things in science. He was a French guy. There were a lot of French and English scientist around this time that we end up learning about. It's the Western science. And he, as you also hear about a lot of people back in the day, like his mom passed away when he was really, really little. He was a member of like the aristocracy, because really only the people that were members of the aristocracy had the luxury of learning and being able to do experiments and being taught things and stuff like that. So as a teenager, he invented one of the first calculators. He's considered to be one of the two people to invent the first calculator. He also studied things with fluids. He did a whole lot in science, including, this may also sound silly to modern ears, but he wrote a very important paper defending the scientific method. You know, it's kind of a silly thing to think of today that people would need to defend the scientific method, but like I said, times were different back then. There were a lot of philosophies that if you just thought something was true, then it would be true. And the scientific method went against that, because you actually had to show evidence that things were true. And I guess there's a lot of people today that still think if you think something is true, that it's true. All right, there are 3 scientists that you're going to need to know about, and the laws named after them. Pascal doesn't have a law named after him. Pascal just has the unit of pressure named after him. So the 3 people that you're going to have to learn their laws, and you're going to have to remember which law was which, are, one is Boyle. This guy's name is Robert Boyle. And he was the assistant of somebody named Robert Hooke, who you should remember from 7th grade. Robert Hooke was the very first person to ever see a cell. And his work was, it was back in the early 1600s. This guy actually gets credit. You know how you learned about Gregor Mendel being like the father of genetics, and you know the father of taxonomy, and the first people who did this or that you learned about in the past. This guy his title is he is the first modern chemist. So apparently Robert Boyle is considered to be the first person to practice modern chemistry. He was an alchemist back in the day. He was one of the people that was trying to figure out how to change metals like silver into gold or lead into gold. But the work that he's most famous for, and that he has the law named after, is Boyle's Law. And Boyle's Law states that when the pressure of a gas increases, its volume decreases. And there's a flip side to that too. If the pressure on the gas decreases, its volume would increase. And one of the things that he designed to be able to do this was a special pump. It was like a big glass kind of globe, and he could use a piston to push air out and then turn a valve and not let it back in and then pull the piston. So he could actually like force air in or force air out of this big globe, and you could put things in the globe and see what would happen. A little bit like a vacuum chamber like you would see today in science classes. The second guy is Charles. His name is Jacque Charles. And he was another French guy, and he was a pioneer hot air ballooner. And the law named after him states that when temperature increases, volume increases. So what's this one missing that the other one doesn't have? So this one's about temperature and about volume. Well, that last one, if we go back and take a look, remember, was about pressure and volume. And what you're going to notice with these 3 gas laws is that there are 3 variables, as we mentioned a few minutes ago, 3 variables that dictate the behaviors of gases, and they are pressure, temperature, and volume. So with each of these 3 laws, the one that's missing, so if this one is pressure and volume, what's missing from here is temperature. That means that that one needs to be constant. So the way this law works is at a constant temperature, if you increase the pressure, then the volume will get smaller. And then Charles's law, since it is about temperature and volume, that pressure is being maintained. So pressure is the same. And when pressure is the same, if you increase the temperature, well, the volume gets bigger. Some interesting things about Charles is he was one of the first people to ever go up in a This isn't a hot air balloon. Hot air balloons were actually a little bit different. Charles's law was based, and hot air balloons were happening at the same time, but Charles's law, Jacque Charles, his experiments were based around hydrogen balloons. So they would amass a bunch of hydrogen, put it in a balloon, and see what it would do. He was one of the first people to actually go up in a balloon. He went up with a couple of other people, and they went up pretty high. They went up like 1,800 feet, and then came back down, and he was like, this is fantastic. A few months before they did that, there were experiments where people sent a balloon up, a hydrogen-filled balloon up, and then it came back down, and it landed in a little village, and it freaked the people in the village out so much that they attacked it with pitchforks and destroyed the balloon because, well, this was a long time ago. This was like the mid-1700s, so that would have been very freaky to see something float out of the sky and land in your village back then. And then Jacques got so excited after doing that first one that he designed another one, and something went a little bit wrong with the amount of hydrogen that they were able to get, so he went up by himself. And instead of going up the 1,800 feet that they went up the last time, he actually went up too fast. And this was like a big deal. There were thousands of people around. They actually sold tickets to come see him lift off. Benjamin Franklin was there to watch him lift off. And he accelerated a little bit too quickly. He ascended too quickly, ended up going up to about 10,000 feet. When he came back down, he had like massive ear pain and headaches and stuff like that. And when he was going up, he said that he was giving up the earth and he was going to stay in the air forever because it was so much fun. And then he actually never went up in a balloon again. That was his last trip. He only went up those really 2 times. But 10,000 feet, one of the phenomenons that he saw on that trip was when he was rising, the sun set. And then he went up so quickly that he saw the sun rise and then watched the sun set again. So I don't know. I can't imagine anybody else would have really been able to ever do that before him. That might be the first double sunset ever seen. The third guy is named Gay Lussac. His name was Joseph Gay Lussac. And he did a lot of really interesting things too. He was more late 1700s. So while Boyle was first, Jacque Charles was about 100 years later, and then this guy was 50 to 60 years later or so, we'll say. So there's this kind of like sequence of discovery going on. And his law is based around, well, the other 2 variables we haven't discussed, so temperature and pressure. So that means which variable is staying put, which variable is staying constant. If this is about temperature and pressure, well, it must be the other one, which is volume. So if volume is the same, and you increase the temperature, well, the pressure goes up. All of this makes sense if you think back to how the particles are behaving in there because of the thermal energy. So in this case, if the volume is the same, if the size of the container is the same, and we increase the temperature, so in other words, we make the particles move faster, well, the particles are going to be slamming into the glass container more often and at greater speed, which would increase the pressure. So all 3 of these laws are really just talking about and explaining how the molecules are behaving and how we would measure them under different changes. Now, what's really interesting, I think anyway, from a historical perspective, we call this one Charles's Law, but he actually didn't really put it together. It's based on unpublished work that was discovered and read by this guy. So Joseph Gay Lussac actually published Charles's Law and gave Charles credit for it because he had seen the unpublished work. So he had kind of done it first, which is really unique. Usually if it's not published, then it doesn't belong to you and someone else can publish it and get credit for it. So he could have credit for 2 gas laws, but he did an honorable thing and made sure that Charles got the credit that he deserved for his work, which was very cool. All right, so we have some quick checks. You're going to have to be able to use graphs to identify which law is which, and maybe I'll give you a little memory tool to try to remember. So one of the best ways to memorize things, there's several different techniques for memorizing things, but one useful kind of technique is to try to apply other words to the situation. So for example, if Boyle's law, let me pick something that's not yellow. We'll go green. If Boyle's law says talks about volume and pressure, remember as volume goes up, pressure goes down, vice versa. You can, if you try to like come up with words that can connect all three of those things together, it helps you remember it. So there was a comic strip back when I was a kid called Prince Valiant. So we have Prince Valiant, and that picture of Boyle, I think really looks like Prince Valiant. So that helps me remember that Boyle did volume and pressure. But that's not going to mean anything to you because you've never seen the comic strip of Prince Valiant, but that's how I remembered it when I was in school. So you can also come up with other things. So his name is Boyle. It's not spelled the same, but there were terrible diseases in the past that if you got them, you got covered in boils. And I can imagine that that would have a lot of vomiting and pain associated with it. So you got to come up with like a little memory trick to try to link the letters P and V to B. And if you do that, well, you can remember that Boyle is volume and pressure. And you can do the same thing for the other two as well. So Charles, when I was a kid, when I was a teenager, after school I'd go home, there was a show on called Charles in Charge. And it was must-see TV. You didn't miss an episode of Charles in Charge. So that's how I remember that Charles is temperature and volume. But you obviously should come up with something that relates more to you, because I am certain that none of you know the show Charles in Charge. And the last one, Gay-Lussac's law, his has to do with pressure and temperature. Well, P and T is like a punctuation point, and Gay-Lussac's last name has a hyphen in it. So that's how I remember that Gay-Lussac's law has to do with pressure and temperature, because it has a punctuation point in his name. So, back to the quick checks. In class, I'll call and you'll have to say which of these graphs is going with which of those gas laws. And you'll have to do the very same thing on a quiz. You're going to see a graph, or it's going to describe what's happening in a situation, and you'll have to identify the gas law that goes along with it. So we got this one, we got this graph, and we've got this graph. All right, so let's apply some of these gas laws to things. Heat engines are the name given to any machine that turns heat energy or thermal energy into mechanical energy. So if you can use thermal energy, which is the motion of the molecules and particles, to make something actually move in a larger world, not the molecules themselves, but actually use those rapidly moving molecules to move something larger that we can see with our eyes, you have a heat engine. And there's two normal kinds of heat engines that that you'll come across. They are external and internal. So the external combustion engine, well, if it's external, that means the outside. If it's combustion, it means things are burning. So if things are burning outside of the engine, then you have an external combustion engine. And this was used for years and years and years and years and years for steam engines. So in steam engines, you would burn the coal. The engine itself is over here. All right, so you would burn the coal over here. It's outside of the engine, and you use the heat from that burning coal to boil water. When you boil water, the water turns into steam. Steam is going really fast. Remember, the molecules of water can't get any higher than 100 degrees Celsius, but steam can. So the steam gets going really, really hot. The particles start moving a lot. You are building up the temperature. So the volume is the same. You're building up pressure until you get enough pressure that you can push on this piston. And when you push on the piston, that turns the wheels. That's how a steam engine works. So the heat from the coal heats up the water, which heats up the air, which pushes on the piston. Thanks, Thomas. You're very useful. Modern day cars, though, use internal combustion engines. If you watch a car work, you can't actually see the fire like you could in a steam engine, in a coal engine. So all the burning is happening inside the motor. And this is a neat diagram here that shows you what's actually happening. Now remember, this is happening super fast. If you look at a gauge on your car, you see the RPMs. That means rotations per minute. And that's how fast this thing is going around. All right, so if it's 5,000, or we'll just say 6,000 rotations per minute, like that's a lot. All right, this thing is flying around. So what we're going to talk about slowly in steps is happening at a very, very, very high pace. So in this one, you are burning gasoline. So the gasoline comes in, this intake valve thing here opens up. So a valve is just a doorway. A valve is a doorway that can open and close. So in the first step, this doorway opens, this little valve opens, and air mixed with gas comes in and fills up this chamber. So we can see the air particles and the gas particles mixed together in this chamber. And when that's in the situation, the piston is in a down position here. And then the crankshaft is actually what goes and turns the wheels, in case you're wondering what that is. So the next step along the way, the valve closes. So now this chamber is sealed. It's stuck. Remember, the motor and the engine's turning, so this thing is going around the whole time. It's being pushed around by this, but it still continues to go. So, and the next step, this thing goes down, and it pushes up on the chamber. So these are sealed, so nothing can really happen here except the volume is getting smaller. And that causes the particles to get closer together to each other, and that increases the pressure a lot. So this is the compression step. And in cars or in your like lawnmower or things like that, if you lose this compression step, then you don't get the work that you want. And then after it's fully compressed, the spark plug fires, and that causes the air in the gas to ignite and actually have your moment of fire. And when that happens, well, it puts a lot of pressure and heat, and that blows the piston back down. And when it blows the piston back down, that causes it to crank around. And that's actually the power force. That's where you get the power that's cranking the tires around to heat up. And then when it blows it back down, you still have all this pressure there. And then the exhaust valve opens, and then this is your exhaust. And that ends up going out your exhaust pipe. And then the whole thing repeats itself. That valve closes, this valve opens, and it fills back up. That's how your car motor works. So if you think about each one of these steps, the different gas laws can be applied. And they all kind of work together and sometimes, because remember, the gas laws, one of those variables has to remain constant in order for it to be true. But in real life, it's hard to keep one variable constant. So you have to think about how they all start to work together. The other way we can apply this is not into an engine, which makes things move, but how else can we apply the gas laws? And this is how your refrigerator works. So your refrigerator works by combining all of the things together that we've learned so far in Unit 2. It has to do with thermal energy and the transfer of energy and phase changes and the gas laws. So refrigerators work by pumping the heat found in your food. So you usually don't think of heat being found in your food except for if it's not hot enough when you're eating it. But all of your food, just like you, have a heat level inside of you. And it pumps that heat from the food from inside the fridge into the air of the room. So what a refrigerator does is it actually pumps heat out into the room outside. And it does it through a series of steps. So step one, you have these pipes inside your fridge, inside the walls of your fridge. And they are there, they contain a liquid, a special liquid called a refrigerant. And the refrigerant can evaporate at really low boiling points. So it would normally be a gas, if you want to think about it that way. So Freon is a good example. Like Freon is normally a gas under normal conditions. It takes a very small temperature to turn it from a liquid into a gas. So at this stage, though, it's a liquid in here, and it's inside your refrigerator. So the heat in your food, so the heat in your gallon of milk or the heat in your bag of peas that you put in the freezer, the amount of latent heat inside that is enough to make this liquid boil. And it boils in a step called the evaporator, because that's what you call it when something goes from a liquid to a gas. And so the heat from your food evaporates the liquid into a gas, and then that gas moves down to a step down here to something called a compressor. Now this is what you actually plug your refrigerator in to do. This takes power. So this requires electricity to run. In the old days, before there was, I'm going to say, electricity or reliable electricity, like the earliest refrigerators that they would have in like apartments in New York City and stuff like that actually ran on a flame. They were gas powered. This step down here would happen due to, a little jet of flame coming out. But anyway, the compressor squeezes the the gas. And it puts pressure on the gas. Well, because of the gas laws, if the volume's not going to change and you're squeezing the gas, you're adding pressure to it, it makes the temperature go up. So now we have this coolant with a really low boiling point that's already absorbed heat from food, now being turned into a much warmer gas because of the compressor. And then it leaves the fridge and it goes out to the spot behind the fridge. Now, if you've never pulled your fridge out and looked at the back, you should take a look at the refrigerator that we have in class and look at the back of it. You have these wires and all these pipes that kind of snake around all over the place. This step is called the condenser, because this is where the heat leaves that gas, the coolant gas, and the heat leaves that and goes into the cooler place, because thermal energy always moves from an area where it's a higher temperature to lower temperature, or an area where it's warmer to where it's cooler. So the reason that you have to do this step down here is to make sure you're making that gas warmer than the air in the room. So if it's warmer than the air in the room, the heat's going to leave the gas and go into the room. And when it does that, it can drop its temperature back down to the point where it can turn back into the liquid. It actually does that up here. So after it goes through all of that, it goes through something called an expansion valve. That reduces the amount of pressure, and it allows everything to kind of expand. And that drops the temperature enough that it can turn back into a liquid, and then it repeats the process all over again. When a refrigerator or a freezer breaks, it's almost always because this thing down here wears out, breaks. So rarely do you have leaks in Freon, although that can happen, but usually it's because your compressor wears out and dies, and then your refrigerator doesn't work. A couple fun facts about this. My father moved down to South Carolina. My parents moved down to South Carolina, and he it gets really hot down there. His garage is like 100 degrees. It's insane. And he put a refrigerator out there, and he was having a hard time keeping the things in the refrigerator cold. And he was like, refrigerator just won't work. I get another refrigerator, and it also doesn't work. Well, that's because the garage is so hot that the air in the garage is like 100 degrees. The air in the garage is warmer than what the compressor is able to make the temperature of this liquid, so you're not getting any heat actually pumping out. That's like trying to, run water uphill. So in a really hot room, a refrigerator can't work. All right, booby trap, 11 questions. Good luck. See you in class.